In question 4, we're given the function h of x equal to 3 over 2 minus x, and we're asked to calculate some compositions of functions, as well as an inverse of a function. So first we're asked to calculate the inverse of h of x. Remember, when we calculate an inverse, we essentially swap x and y and then solve for y. So we're going to say x equals 3 over 2 minus y. Now, the y is in the denominator. Anytime something's in the denominator and we need it not to be, we can multiply both sides by that denominator to clear the denominator. On this side, it gives us x times 2 minus y equals, and then on the other side, it gives us equals 3. Now, your first instinct will probably be to distribute, but remember, what we're trying to do is get y alone. If I distribute, I'm getting the x even closer to the y, which is actually creating new problems instead of simplifying the situation. So what I actually want to do next is divide both sides by x so that the x will leave this side. That leaves me with 2 minus y equals 3 divided by x. To continue to try to get y alone, I next want to subtract 2 from each side. So negative y equals 3 over x minus 2. Y is almost alone, but not quite. So I'm going to need to multiply both sides by negative 1 to eliminate that negative sign and get y completely alone. So if I multiply both sides by negative 1, I have y is equal to, now I have some options. I can write negative 3x plus 2. That feels a little bit awkward. So when I go to write my final answer, I'm going to switch back to inverse notation. So h inverse of x equals, and I'm actually going to flip my problem around and say 2 minus 3 over x. Now, if you don't flip the problem around, that's totally fine. You can leave it as negative 3 over x plus 2. For me, that just feels a little bit more awkward. So I like to flip it around. And here is my inverse of h of x. Next, I'm asked to do a composition. H composition, h inverse of 3. Now, if you remember, there's two different notations. This is my least favorite notation. So for myself, I tend to rewrite this when I see it in that notation that shows me that what's happening is first I have to do h inverse of 3 and then take that answer and put it into h of x. So let's do that. H inverse of 3, we're going to get started, tells me to take 3 and put it into h inverse. So that's 2 minus 3 over 3. Well, we know that 3 divided by 3 is 1, and 2 minus 1 is also 1. So h inverse of 3 equals 1. So now I'm ready to do h of that 1 that we just found. Well, going back to the original equation, we have 3 over 2 minus 1. That's 3 over 1, or just 3. Now we want to notice what happened. We started with an input of 3, and we ended with an output of 3. It's kind of interesting that what we originally put in is what we got out. It seems like that's probably not a coincidence. Let's look at question C. Notice it's very, very similar. We're just being asked to do the composition in the opposite order. And we know that order matters with compositions. It's not commutative like multiplication. So this is h inverse of h of 3. So in this case, I'm going to start inside with h of 3. So h of 3 says take 3 and put it in place of x. So that's going to be 3 over 2 minus 3. Or 3 over negative 1, which is negative 3. So negative 3 is that value, h of 3. So now I can go in and say I'm supposed to take h inverse of that negative 3. Well, when I do that, remember h inverse was over here. 2 minus 3 divided by that negative 3. 2 minus 3 divided by negative 3. Well, a negative and a negative make a positive. So this is 2 plus 3 divided by 3 is 1, or 3. Notice it happened again. Our input was 3 and our output was 3. That's clearly not a coincidence because it seems to have happened twice. So what are they trying to tell us here? Well, when we look at this pair, we can see an important rule. If two functions or relations are inverses, then f of f inverse of x will equal x. In other words, whatever I put in, I'm also going to get out. And if I do it in the other order, f inverse of f of x will also equal x. So a function and its inverse have to completely undo each other. So if f inverse does a bunch of things to x, and then I take f of that answer, it undoes all the things that f inverse had done, and it leads me back to my original input. Now, we're asked here, when we did B and C, I had you plug in 3 both times. And in question D, I asked, why couldn't we use 0 or 2 in parts B and C? So let's look and see what would happen. If I did h of 0, I would get 3 over 2 minus 0, which is 3 over 2. There's no issue there. But if I do h inverse of 0, I would say 2 minus 3 over 0, and that's undefined. We can't do that. So 0 is not in the domain of h inverse. So I can't use 0 to test and see what's going on because it's not in the domain of the inverse. Let's look and see what happens if I use 2. Well, h of 2 would be 3 over 2 minus 2, which is, 3 over 0. That's also undefined. So it doesn't really matter what would happen when I plug it in to h inverse because it's already not an option. So 2 is not in the domain of h of x. So we wouldn't be able to use either of those numbers to test to see if something's an inverse or not because they're not in the domain of one of the functions that we're working with. So I'm actually realizing that all of this that I wrote right here, that belonged on this line down here. Composition of inverse functions says if I compose a function and its inverse, I'm going to get x, no matter which order I do that in. And that's what I just explained in purple just a moment ago. All right, this last little bit is probably only going to come up in like one question on your homework. So this isn't the most important thing you're going to learn in this unit, but I need you to have heard of a one-to-one function. So I included it here on the note sheet. So a one-to-one function is defined as a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. This is kind of even stronger than just being a function. So something's a function if each x has only one y. In other words, if I put a number in, I can only get one answer out. And we were able to test that visually on a graph with the vertical line test. One-to-one says, okay, it's already a function because each x has only one y. But also, it's a one-to-one function if each y has only one x. So it goes the other way as well. In other words, every y value has only one x value that can create it. So this is a subset of all functions. If you look down below, I said, how is this different from being a relation? Well, a function is a relation between two sets of real numbers such that each element of the domain corresponds to exactly one number in the range. That's what I just described here. This is different because in 1-to-1 it also goes the other way. And then I asked, what does this have to do with the inverse of a function being a relation or a function? How does it relate to the horizontal line test? So you might remember earlier on when I was giving these notes, I mentioned that we can use the horizontal line test to predict what's going on. If a function is 1-to-1, its inverse will also be a function. So a function that passes both the vertical and horizontal line tests is a 1-to-1 function. All right, let's do the last example on this note sheet. Find the inverse of the function by identifying an appropriate restriction of the domain. In other words, find the inverse, but restrict the domain of the function to ensure that the inverse will also be a function. All right, let's look at this. Says, I've got this function f of x equals x squared minus 6 plus 9. So we know this is a parabola that opens up. So we've already talked today about the fact that the inverse of this would look like a parabola that would open to the side because it would reflect across that line y equals x. While this one is a function, this one is not. So we have to restrict the domain so that when we reflect it, it becomes a function. So if I think about that, if I take only the right-hand side, when I reflect across this line, I will get only the top portion of the parabola. And that way, both the original function and its inverse can be functions. So we need to figure out, how do we restrict this domain? Well, you've got some options, but you guys know how to factor and how to complete the square. Basically, we need to convert this to vertex form because I need to know what that vertex is to know how to restrict my domain. So let's look at this. If I have f of x equals x squared minus 6x plus 9, you might recognize this as a perfect square trinomial, but if you don't, you could factor it. I would say, what multiplies to make 9 and adds to make negative 6? Well, that would be a negative 3 and another negative 3. So when we split that middle term, we have x squared minus 3x plus 9. We take a GCF of x out of the first two terms and a GCF of negative 3 out of the last two terms. Notice they have that x minus 3 in common, and the other factor also happens to be x minus 3. So in vertex form, we have x minus 3 all squared. We can identify that the vertex of this parabola is at 3, 0. Well, now I know how to restrict my domain. If this vertex is at 3, 0, I need all of the x values to be 3 or bigger. So if I restrict my domain to x is greater than or equal to 3, the inverse will be a function. So I am still supposed to find that inverse. So we need to do the typical process of swapping x and y. So x equals y squared minus 6y plus 9. But notice that's a little awkward to solve. Let's make use of this factored form we came up with. If instead I say x equals x minus 3 squared, whoops, I'm sorry, it's going to be y minus 3 squared because we swapped x and y. I can take the square root of each side, which would normally give me a plus or minus over here. But remember, our whole purpose was that we only wanted the top part so that we could get a function. So we are going to leave out the minus so that we only get the top part of the graph. So when I add 3 to both sides, I have that f inverse of x will equal 3 plus root x. So I have a radical that's basically translated up 3, and that will be an inverse, my function that is an inverse that is a function, because we restricted the original domain so that we would only get the top when we did the reflection across y equals x.